Welcome back. In this video, we're going to go through an introduction to multivariable calculus based on a review of single variable calculus from the last video. Just as Math 1A and 1B had a very specific storyline, so too in multivariable calculus, Math 1C and 1D also have a very specific storyline. In particular, multivariable calculus generalizes the ordinary derivative operator specifically in multivariable calculus, we study partial derivatives. Where the word partial means that we're not taking ordinary derivatives of single variable calculus, we're taking partial derivatives of multivariable functions. Where multivariable functions are functions with more than one input variable. Just like we saw in our review of single variable calculus, in multivariable calculus, we're really going to just study two problems. First one I'm going to call the forward problem. And this is going to be only part of Math 1C, which I like to call part 1, which is known as partial differentiation via the gradient operator. And we'll talk a lot more about this as the quarter goes on. For now, it's enough to understand that we have this new derivative operator that's going to act like the single variable derivative operator, except it's going to act on multivariable functions. This is called the gradient operator. This is what we're going to produce in Math 1C. This gradient operator is applied to functions of multivariables. In this case, we'll just look at the easiest multivariable function, which is one of two input variables. But the gradient operator can be applied to multivariable functions with more than two input variables. Okay, so we have this derivative operator that's acting as on a function just like before, except the input function has two variables. And then this is where things get really interesting. The derivative of this multivariable function actually happens to be a vector. And this vector looks something like f sub x of xy and f sub y of xy. These are vector notation parameters, which we'll talk about later. This is the unknown and desired partial derivative of f with respect to x. So here, the first component of this derivative is going to be the partial derivative of the capital F function with respect to the first variable. And then the second component of this is going to be the unknown and desired partial derivative of capital F with respect to y. These are both multivariable derivative functions, and we'll talk a lot more about this. But the idea is that the forward problem in multivariable differentiation is that we take a derivative operator, apply it to a function, and produce a derivative. One of the major changes in multivariable function is that the derivative of a multivariable function is no longer a single function. It's actually a list of functions, each of which is known as a partial derivative. Okay, so this is the forward problem of multivariable calculus. And the backward problem moves along the same structure. This is going to be known as Math 1D, which is known as partial integration, and some people call this multiple integration. Okay, just as before, we start with the same derivative operator. In this case, it's known as the gradient. The gradient is a vector because it produces more than one output function. In the backward problem, instead of me giving you the input and you producing the output, I'm going to say, hey, listen, here is a known output, which is the derivative of some multivariable function. So here's a vector with two functions, one in the first coordinate, one in the second coordinate. And the claim in the backward problem, Math 1D, is this given vector field, it's kind of a formal name for the derivative of a multivariable function, each of whose components is a partial derivative. If you have this given vector field and you have a gradient operator, please produce the unknown multivariable function such that when you take the gradient of that function, you produce that given vector field. These are sometimes known as potential functions, which relates to some of the stuff that you'll see in physics in your future. Functions that when you take their gradient, you get a given vector field. That's called a potential function. And you see that these are the exact opposites of each other. In this case, you take the derivative of a multivariable function, the gradient of that function, and you produce a list of partial derivatives. In the reverse problem, I give you a list of partial derivatives, and then you find the ordinary derivative, you find the multivariable function such that when you take the gradient, you get that list back. Notice this is the same structure as what we did in single variable. It's just done to more interesting functions. The exciting thing is multivariable functions are so much more powerful than single variable functions because they show up in so many more contexts. In the next video, we'll talk about a very, very popular application in which multivariable functions arise. See you in the next video.